today is on a process study for the design of a small 2 Kelvin refrigerator. It's worthwhile going over a few things I have on my slide here in the very first one. This right here was actually, this was written by Sam Collins. It's typically how you see a lot of the cycles that he wrote down when he did them. Very back of the envelope types of things. This is the test refrigerator that before they built the Stanford 1.8K machine, they designed it for 24 watts at 1.8K. And the 1.8K machine was actually the first. It was nominally 300 watts at that temperature. And this is the machine right here. It was built around 1969 or so. And this is the heat exchanger. Basically in the center of it, this is about 7 feet tall. Consists of 4 sections, and it's basically a tube that's wrapped around in a loop, alternating the tube passes go from in to out, and then from out to in, alternating back and forth. And it's a tube with a fin on it. And in the center, this is a PT diagram for helium. So it's worthwhile pointing out a couple things on this. So I mentioned temperature, pressure. This curve right towards the bottom right here, that is actually the liquid vapor curve right there. So on this side you have liquid, on this side you have vapor. The top point here is the critical point, and this is known as a lambda point. It's about 2.17 degrees. And below that point you have helium changes its behavior. It becomes helium-2, which is no longer a normal fluid. And we're not so much interested up here, but in this range, this is much higher pressures. As you can see, this is 10 atmospheres, 20 on up. So our typical range of operation is down in this area right here. So again, for those of you who kind of a little bit of review from the previous sections. Helium, normal boiling point for it at 1 atmosphere is about 4.2 Kelvin. And the critical point, as I mentioned, happens around 2.2 or 2.17 degrees. The lambda transition occurs at that temperature. The density of the liquid of helium-1 at 1 atmosphere and superfluid helium at 2.2 Kelvin normally is about 15% greater. So it's obviously more colder at the colder temperature. And at that colder temperature, that helium superfluid, there are 2 components. There's a normal fluid and a superfluid component. And of course, the superfluid component has no viscosity and no entropy. But it's a mixture of the two. And as also we've mentioned before, typically, this is used for, in our case, superconducting radio frequency and also for superconducting magnets as lubricator. So just to throw up a few slides showing the properties of helium at these colder temperatures. This is the liquid density versus temperature. You can see this point where the slope changes is the lambda point. And this is about 1 atmosphere right in here. So it goes from about 120 to about 145 grams per liter. This is the latent heat versus temperature. Again, this is the lambda point right here. You can see normally we're right in this area. We're about 18 or so joules per gram is the latent heat. The superfluid has much closer to, say, 23 or so joules per gram. And this slide, what it's showing, this is temperature versus the mass fraction of superfluid. So when you this is lambda right here. Obviously, you just have to start to get some superfluid, and as you get colder and colder, you get all the way to you have 100% superfluid. At 1 Kelvin, you roughly have about 99% superfluid. At the temperatures we typically operate here at JLab, we're about 2 Kelvin right here. So we have it's about 43% superfluid. So moving on to the process study. So they were really, for helium, refrigeration of helium below 4.2, there are typically four methods that are used. There's direct vacuum pumping, there's refrigeration recovery, there's using cryogenic centrifugal cold compressors, as we call them, and then a combination of using those cold compressors and warm compression. So some of the compression is done cold, the remaining amount is done warm. The labs, put up here a few of the labs that use, their examples of this. The direct vacuum pumping, Triumph is an example of that, Brookhaven, ERL, refrigeration recovery, Slack, Daisy, the Tesla test facility, and JLab CTF is an example of that. And of course, for all cold compressors, the CVAP and SNS are really two examples for that. And then for the combination, there's quite a few places that use a combination of warm and cold compression. So, the objective of this process study, just to state it out, this process study is centered around the development of a nominally 100 watt, 200 watt range, 2 Kelvin refrigerator capable of working in conjunction with a commercially available 4.5K liquefaction system. And the major subsystems for this small 2K subsystem involve, as I mentioned, about a 2 to 3 gram a second 4K liquefier. It involves a vacuum pumping system. It involves a positive compression system on the order of 10 grams a second, and of course the 2K cold box. The 2K cold box, for this process study, there's no rotating machinery inside the 2K cold box. It only consists of passive components such as heat exchangers and Joule-Thomson, throttling type valves. And the purpose basically is we want to examine a number of process parameters. That is the mass flow imbalance, heat exchanger size, and supply pressure. So just to give I'll discuss this more in detail later, but basically what I'm referring to here is, you'll see this in pictures later on. This is representing the load. So this is the 2 Kelvin nominally liquid. So this represents a heat exchanger. This is the vacuum pump. This is a positive pressure compressor. This represents the 4K liquefier, which consists of the cold box and a compressor. So the flow path for this type of arrangement is the vapor comes from the 2K bath here, is warmed as it exchanges heat with the high pressure stream through these heat exchangers. This right here is just representing an ambient air vaporizer. That's typically what we would use in something like that. It's to make sure that the temperature into the vacuum pump doesn't get too cold. And then it goes to the vacuum pump, so it's subatmospheric here, it's just positive pressure here. It goes from just positive to above positive, 8, 10, 12 bars, something like that. And then it flows back down this side. A portion of the stream goes to the plant, and a portion in here injects it. There are various configurations, so this will change, but just to give you an idea of what you'll be looking at when you see the pictures later on, I wanted to give a description. So this mass flow imbalance here is basically the ratio between the mass flow on this side and the mass flow on this side of this 2K cold box. The heat exchanger sizes are these heat exchangers here, or this one here, for example. And the supply pressure is going to be this supply pressure on this side right here, here, here. Okay, so before we begin in that, we should look at some practical issues that are very important to looking at, are important to the objective, but not directly related to the process study. And those are the first one is the vacuum pump systems that you'll typically try and buy commercially. A number of modifications are necessary to be done on them before you can actually use them. One of them is vacuum pump systems need some extra oil injection help for cooling. You also need a properly designed oil removal system for your positive compressor system. And it's worth mentioning here, which is why it's in red, that is actually very important because that is a very common problem in many systems, and especially for subatmospheric systems, you don't need any more things that will limit the amount of uptime that you have on a 2K machine, because that oil carryover will degrade your ability, degrade your oil removal system, and therefore you can have contamination problems. So some other practical issues here are the mechanical design needs to be considered. We use something called guard vacuum, which probably a number of you are familiar with. It is basically an intercept at a lower pressure than the process pressure between, that those isolate between atmosphere and the process that's in between. That, in addition to good mass spectrometer testing to make sure you don't have leaks, and things such as that are important. Also, very importantly, an integrated helium purifier. A lot of times, one might be tempted to assume that there's contamination is low on the stream, but in practice, that's probably a bad assumption. So in any 2K design, you want to anticipate putting a full flow, or at least a slipstream purifier into the system. So one important thing also before proceeding with the process study is to look at some comparable systems. And two comparables, the only other comparable system to the JLab CTF is a system that was done in Germany, the DAISY Tesla test facility. And I should explain what I mean by comparable. Comparable meaning, as I mentioned in the first part of the first slides, is a distinct, we want to use a commercial liquefier and couple that to this 2K cold box and vacuum pumping system. So some of these systems integrate the heat exchangers into the 4K cold box, so it's a custom 4K cold box design. We're not interested in looking at it in this study. Also, the only data that we could really get a hold of very easily was the JLab CTF data. This was very easy to get a hold of the data from Tesla. So this chart basically shows some comparisons again between the JLab and the DAISY system of what we could find. Load temperature is a little different. JLab's 2.0 and DAISY's 1.8. Nominal loads fairly close, about 180 watts to 200 watts. And I put that grams per second is the 2K mass flow required to provide that refrigeration. It is. The 4K plants that are used, listed up there, Coke 2200 we use, 900 watt 3 turbine. Lindy machine is used for the DAISY system. And we use a 2-stage vacuum pumps at CTF. It's a blower and a ring pump. The DAISY system uses, it's actually a 4-stage, yeah, 4 stages of compression. It's a big skid. And it uses the Libel blowers, the 16,000, 13,000, and 9,001, and it uses the 1200 as the rotary vane. So I think Rouse mentioned this before in his earlier slide, but of course when you look at something, you want to figure out what are you trying to look at if you're looking at an optimum. So in this particular case, there's a number of things to look at. And what we're looking at in particular is we would like to look at the optimization for maximum efficiency. And as also he had mentioned, that this typically will also result in a global optimum for the other optimums. So what are the process parameters we want to look at? Those process parameters consist of 2 different categories. There's fixed process parameters and varied process parameters, meaning things that we're going to not change during the process study and things that we will select a range and vary them over. The fixed ones involve low temperature, 4K system, exergetic efficiency, the isothermal efficiency, heat in leak, subatmospheric stream pressure drop. And the varied process parameters include the mass flow ratio that I mentioned previously, the total number of heat exchanger NTUs, and the supply pressure. And the overall efficiency of this 2K system is influenced by both types of these. So amongst the fixed parameters that we're interested in looking at, the low temperature, we're fixing low temperature at 2 Kelvin, and it's worthwhile putting up the plot here. This is the saturation pressure versus temperature, and the saturation pressure is on a log curve. And what that means, the purpose for doing that is to say that the isothermal input power required for the vacuum pump is going to be proportional to the pressure ratio. So the pressure ratio in this case is essentially this 1 divided by whatever your saturation pressure is. And for us, that's about 35 millibars. So we're looking at roughly a compression ratio of 34, so that's the case. That places us about here on that. The other fixed parameters that we have are the overall exergenic efficiency of the commercial 4K liquefier. And that system, as I mentioned, includes both the cold box and the compressor system. So it's kind of a package deal. If you went out to a commercial supplier and said, I want a 4K liquefier, it would be the whole thing. It would be the cold box and the compressor system. So as I will show you in a minute, some unpublished data, we basically compiled some to get an idea for smaller liquefiers what the exergenic efficiency would be. So in the range of 11 to 13% is what we saw for 2 to 3 grams a second liquefaction. As it's worth mentioning too, as you get higher in liquefaction flow rate, of course, the efficiency will get better. As typically they use more expansion stages. Also, the fixed parameter is the isothermal efficiency of the vacuum pumping system. This is not a very well understood how this varies with the pressure ratio, but based on the data that we have from CTF, this is how we arrived at what we believe that should be, at least for our study. And the parasitic heat leak into the process, we assume 55 watts, just to be conservative, not get too unrealistic numbers. So again, those are fixed parameters. Okay, this chart, real briefly, the important things up here is these are some of the ones we looked at. This is actually, this cryocooler is not a typical small system, but I put it up there just as a reference to see on the very low end what it would be. This is the liquefaction rate in grams per second, and this is the exergenic efficiency. So as you can see, somewhere in the neighborhood of, for the machine size that we're talking about, is 11 to 13%. There's a lot of information in all this, and hopefully I'm going to hit the highlights, and for details, hopefully there's enough information to dig into it later. Feel free to ask me questions on any of that in there, now or later. The other fixed parameter is the subatmospheric pressure drop, and what we're going to assume is that that pressure drop is proportional to the number of heat exchanger entities. So our assumption here, which is that we're taking here, is that the NTUs is proportional to heat exchanger length, which is correct. And the more subatmospheric pressure drop you have, of course, the larger vacuum pump you need, because your pressure ratio increases. As far as varied parameters, I've mentioned those in that chart before. We'll go over these again, but it's the mass flow ratio from the high stream to the low stream. We vary this from 40 to 100% as the solution allowed. This is also called flow imbalance. We varied the total number of heat exchanger NTUs from 20 to 45. And we didn't go greater than 45 because we felt like that wouldn't be very realistic. The subatmospheric pressure drop would be too excessive beyond 45 NTUs. As far as the supply pressure for the 2K cold box, the supply pressure, we vary from 6 to 18 atmospheres as well. Okay, it's worth talking too about helium-specific heat capacity in the heat exchangers. So the C/P, which is the heat capacity at constant pressure for helium, is for the real fluid is very non-constant for the range that we're interested in. you'll see this both in the graph that I put up in a minute and also in heat exchanger cooling curves, which we'll discuss later. But we can't, the bottom line is we can't ignore, we can't assume a constant CCP. That would lead to wrong solution. So we do look at the real CCP behavior in the heat exchanger calculations. And another thing I have down here at the bottom, theoretically, the most reversible stream temperature difference, this delta T, this is the temperature difference. So if you took a cross-section cut of the heat exchanger and the temperature difference between the high-pressure stream and the low-pressure stream, that's what this means here. That ratio equal to a constant is theoretically the most reversible stream distribution. This right here is a plot to give you an idea of the CCP of helium. So here the temperature, CCP, you can see this is 100 Kelvin. It gets very interesting once you get down here. And you can see it has this very strong effect on the pressure as well. It gets much more pronounced the closer you get to the critical pressure. So the critical pressure, as we mentioned, is about 2.3 or so. So this is 3 atmospheres. And you can see 3 atmospheres, 6 atmospheres. This peak subsides a bit as you move away from that critical point. And this right here, of course, is at lambda. So that's the other abrupt change you see. The point is the non-ideality of the CCP. So, as I mentioned, since the ideal temperature difference in the heat exchanger, that distribution is in actuality quite different than what we would like it to be. It's actually a logarithmic distribution. To deal with this, we need longer heat exchangers, and that longer heat exchanger reduces that temperature difference, or allows us to get to a lower temperature difference, but it also increases the pressure drop as well. And but we'll say that fortunately that this effect of this pressure drop loss in heat exchanger, although it does affect the vacuum pump size that you have to have, it does not have a very significant effect on the power loss due to the pressure drop. A good design guide, I think as Rouse mentioned before, is to maintain at least 1 meter per 10 NTUs of heat exchanger length. That's for brazed aluminum heat exchangers. And to make sure your pressure drop, your delta P over P, is no more than 25%. So for model characterizations, component characterizations, I used, for the fluid, I used heat pack and gas pack. Some of you will be aware of that. If not, you can Google it and find those properties available for sale. But for the 4K liquefaction system, the exergetic efficiency for large systems is typically going to be about 25%. And for, as I mentioned, for the process study we're doing, we're going to assume 10%. So that range we saw was 10 to 13%, but we're going to pick 10%. And it's also worth mentioning that the exergetic efficiency of that 4K plant is a very strong variable in regards to the overall efficiency of the 2K system. So the better that efficiency, the better your 2K efficiency. Also, we'll assume that the supply pressure is supercritical, and mention that a lot of smaller systems don't use supercritical supply. They'll use saturated liquid supply or subcooled liquid supply. These pictures right here, this is a Air Liquide small liquefier, probably on the order of 700 watts, 800 watts. This is a Lindy system over here, comparable size as well. So, continue with the component characterizations for the vacuum pumping system. We're assuming for this study that 14.5% for the isothermal efficiency. That's based upon data that we gathered from our CTF vacuum pumping system. And the compression system, typically is going to be a rotary screw compressor, and we have good data on that. And this is basically the equation we're using to model the thermal efficiency for that compression system. So you can see it is a function of pressure ratio. This is a picture basically of some of the components, not all of them, but this is a rotary screw compressor. It used to be known as Dunham-Bush. It's now being Hartford is the name on it. That's a twin screw oil-flooded screw compressor, and it's hermetically sealed. See the screw there. You can see the vacuum pumping system. This is a two-stage liquid ring pump. It's got these little paddle wheels that are characteristic of a liquid ring pump. And then this is probably a lot of you are familiar with. This is a blower. It's got these two things here rotate around each other. The ones that we use over at CTF are very large. They're not maybe a little deceiving the size here. For heat exchangers, we also wanted to consider what the effective pressure drop would be in a subatmospheric stream. So we modeled that, as I showed it there, basically as a function of the heat exchanger length. So it would vary between roughly 4 millibar and 9 millibars as we vary the heat exchanger from 20 to 45 NTUs. And I already mentioned that the UA and NTU calculations were done using an integrated cooling curve, since that C sub P is non-linear. And for those who are interested in how that works, the book, Cryogenic Heat Exchange by Barron, he outlines that in there. So this is give you an idea, basically, heat exchangers for those who haven't seen it. This is an aluminum braze heat exchanger. I showed you the pancake coil type that was used in the St. Collins's refrigerator. These are more common to larger systems, and they can also be made in small sizes as well. But basically, it's a number of layers sandwiched with a plate in between. These are the corrugations, a variety of different corrugations. These heat exchangers are very nice. You can tailor both the characteristics you want for both streams, which is very nice. You can't do that, for example, on plate heat exchangers. Okay, for some background information, or for definitional information, exergy. So I talk about exergy, what do I mean? Exergy, if we use that quantity, it's useful for basically quantifying how the input power is utilized in the process. So if you put 1 megawatt to the process, where is that 1 megawatt going? You should be able to, like your budget, you should for your house, you should be able to subdivide where everything is going. What component, how much power each component is using. So that quantity is, that quantity is here. The exergy is equal to enthalpy minus, this is a reference temperature, typically 300 K, times the entropy. It's a physical quantity. So for a system like this where you have this H stream and this L stream, and you want to know what the exergy or reversible work that's required for this, it's just simply mass flow rate times the exergy minus the mass flow rate times the exergy, which is right here. So I've mentioned a number of times exergetic efficiency. I've used that word. So in case, for those of you who I think Rao mentioned this in his previous lecture, or in his previous lectures, but sometimes we'll call it the Carnot efficiency. That's loose terminology. It could be. It's probably better to call it the efficiency as compared to Carnot. It's the ratio of the reversible input power that's required by a load to the actual input power required. And coefficient of performance, inverse coefficient of performance, talked about those two. So in this study, we're going to use 2 different kinds of inverse coefficient of performances. We're going to use one that's called the real COP inverse, and one that's used the ideal COP inverse. The real one is the actual input power divided by the load. So if this is the loads that we're talking about, that's 200 watts, and this is a megawatt. This would be 1 megawatt divided by 200 watts here. That would be the COP inverse. Now, the ideal COP inverse is, I just mentioned, or I just described how we calculate exergy. This would be the exergy flux supplied to the cold box divided by the load, heat load. And there is a, we do that for in examining those two different COPs, it helps us to see the different aspects, which I'll get into. Most of this already. All right. So the first one, the first 2K configuration that we should look at is the most commonly done, and it's what we normally known as direct vacuum pumping. So in this case, what's happening here? This is the 2K bath. We're going to pump. We're going to pump on the 2K bath. We're going to pump on the 2K bath from the vacuum pump right here. So this vaporizer just warms it up from 2 Kelvin up to 300 Kelvin, pressurizes it up to 1 atmosphere, feeds it to the 4K plant, which then liquefies it, and coming out here you have basically we're going to assume 3 atmosphere, 4.5K liquid, which is, that enthalpy is really close to liquid enthalpy, and then that's supplied into the load again. So I mentioned this is very common. It's probably maybe a reasonable thing to do for very small, infrequently done things, on the order of 50 watts. Really a cost analysis should be done to verify that's the case. So for this plant right here, the ideal COP inverse is on the order of 700 watts per watt, and the real COP inverse is on the order of 6,500 watts per watt. So we'll want to remember those. Now, if we introduce, same thing we had before, but we introduce this heat exchanger right here. This heat exchanger is going to, basically this is 4K here and this is 2K here. So if we introduce just that small heat exchanger, we can reduce the COP inverse basically by 30 to 35%. I'll show you a graph on this other side here. So this graph right here is the heat exchanger NTUs that I mentioned, and then this is the COP inverse. The blue line is the ideal, and this magenta line is the real. So it has a very dramatic effect on improving your process performance. And it's also worth noting that once you get past about 2 NTUs, most of your bang for your buck is right here. You get a little bit more out this way, but not a whole lot more. So why are we looking at direct vacuum pumping other than the fact that it's also one of the things that's commonly used? We want to be able to provide an upper bound for our process study on what we would be expecting for results. As a lower limit on the COP inverse, we can look to basically a larger 2K system that uses an efficient 4K liquefier, and those are typically going to be, say, 900 watts per watt. And that's assuming that you have a liquefier that is 25% current. I put this little note down here. This is worth noting that using cold compressors with small systems like we're talking about might not necessarily be more efficient than using refrigeration coverage, which we'll discuss. So just introducing cold compressors in small systems may not necessarily get you better. So comparable 2K systems, we mentioned we're using the JLab CTF to help us out in that. Its real COP inverse is on the order of 3,400 watts per watt. Now, I'll quantify that to say that that's the way it should ideally behave. That's not actually, there's some other issues with CTF why it doesn't get that. But if it was done correctly, it should get 3,400 watts per watt. So in our study, we're looking for something that's much less than 4,200, which is our direct vacuum pumping. Probably less than 3,400, we would hope, but greater than 900. This slide basically lists all of the process model simulation. I think we've covered most of that. If there's something that you're interested in, you can touch back on that later. So this is the first configuration that we looked at. And you've seen this one at the beginning. So this is, again, this is the load. This is the vapor coming through the heat exchangers, warmed up to 300K by the time it reaches the suction of the vacuum pump, pressurized up to 1 atmosphere, then pressurized up to some higher pressure, which will vary this pressure right here, and then it's counterflowed back down this way. So this heat exchanger sees an imbalance. This is the flow ratio we were talking about, high stream to low stream. That's an important parameter that we'll look at. This supply pressure is an important parameter that we'll vary and look at. And the total NTUs of these heat exchangers, basically how long these heat exchangers are, we'll look at as well. And then this is the 4K system, so it basically gets 1 atmosphere helium in and then spits out 3 atmosphere, 4.5K, essentially saturated liquid out here. That slide's just a description of what I went through. This is just to say there's a lot of parameter, there's a lot of calculations that are done. This is an example of one of the calculations done for this process. This is the second configuration that we looked at. And in this configuration, what we have here, what we added in here was this section up here. And the reason we added that is, as I mentioned, it's really important in 2K systems to deal with contamination properly. And chances are that you do have to deal with them. And so by integrating in this type of thing, this basically is a purifier, freeze-out purifier. And in doing this, we've integrated this into the 2K cold box. So this heat exchanger has balanced flow, but we inject it back in here, and then this becomes imbalanced again in this heat exchanger. Other than that, it's very similar to the one we looked at before. I will mention too, there is a loss mechanism right here because this is high pressure, and we're having to inject this to the low pressure stream of the liquefier. Otherwise, it's possible you could match it to the high, but it's difficult, except on a specific instance to be able to do that. So we just assumed that it was dropped. The high pressure was dropped to low pressure. That's just a description. We talked through the previous slides. That's a description of that. And you can look at this later. That's again a sample calculation that was done of that configuration. So the last configuration that we looked at is this one. Now, this one there's a bit more going on here, and the difference is down at this end. The reason is, and we'll be able to see this a little bit clearer later, is the CCP, as I mentioned, the helium is very nonlinear in this region, and what we're trying to do by either injecting it here or injecting it here, and injecting this, so when this stream right here comes around as an injected here, this is injected here from the 4K box. And likewise, when this stream is injected up here, this is injected there. So what we're trying to do in doing that is to see if there's some way we can get better match the cooling curves in these heat exchangers right here. That. All right, so process model results. Basically, those 3 configurations, and also the direct vacuum pump configuration, we're using that as a reference. For all of those, we looked at the following slides we're going to go through. Basically, we're done at 12 atmospheres. We did them at a range of pressures, but the ones I'm going to show you, so we don't throw a million of these things, are at 12 atmospheres. And that the behavior that you'll see is roughly the same whether or not that was 6 atmospheres or 16 atmospheres. It gives you the same basic idea. There'll be a 12 atmosphere supply pressure. And we vary the flow ratio between 40 and 100% as the solution allowed. And as mentioned, the total heat exchanger NTUs were between 20 and 45. So this is that first configuration, a very simple refrigeration recovery configuration. And what we'll see in this curve right here is that there is a minimum. And that minimum corresponds for each total number of heat exchanger NTUs. For this case, for instance, for 35 NTUs, you have that curve right there. And there is an optimum right there. So this is the flow ratio, and this is, I didn't mention, this is the ideal COP inverse. We'll look at the real and ideal COP inverse. So this flow ratio, basically, this is typical of all of them. There's a linear here behavior here, and then it changes very quickly past this optimum. This is the one with the LN2 that was basically integrated purifier. You can see that it has a little bit more, these curves are a little bit higher up and they're a little bit more rounded. And then this is the one where we did that different injection at the cold end heat exchanger. And same basic behavior, curves are much more rounded now. This is the real COP inverse. The difference between this one and the ideal one that we looked at before is this one is more, this has got more of a need to it. Likewise with this one, and likewise with that one. So those were the three ideal COP inverse for those configurations, and then the 3 real ones. So if we take all, as I mentioned, that was done at 12 atmospheres. So if we want to combine all that information. We want to look at what that optimum point is for the total number of heat exchanger NTUs for each one of the pressures. So instead of that whole curve, we want to look at what that optimum point is. And we'd like to look at what that looks like as far as curves. So for the ideal COP inverse for the first configuration, this is an example of what it looks like. And they'll basically all look the same. This curve right here is going to be this is total heat exchanger NTUs on this axis. So we vary from 20 to 45. And this axis is the minimum ideal COP inverse. So that was that point in the mean of the curve. So that's this curve right here, and that's for each pressure. So we vary the pressures from 6, 9, 12, 15, 18, each one of the pressures you can see here. These curves up here correspond to this axis, and this is the flow ratio, that high stream to low stream flow ratio. So at that optimum point, what is the flow ratio? And we can just go through it. They are all pretty similar. These are ideal one for the one for the integrated purifier, and this is the ideal COP inverse for the one that has the heat exchanger that has the varying injection point. And then this is the real COP inverse for the simple refrigeration recovery. The real COP inverse for the one that has the integrated purifier, and the real COP inverse for the one that has the varying injection on the heat exchangers. So I'm going to go back to this one. So I think some of for the real COP inverse, which I'll focus on here in a moment, or right now, the curve that has the best or the lowest COP inverse basically is always going to be pressure that's right around 12 atmospheres. And there's a reason for that. And actually, that was covered in one of Ralph's first lectures when we looked at an ideal refrigerator. An ideal refrigerator operates right around 10 to 12 atmosphere range. So that's something that we would expect. That basically summarizes the some more details of the results. I don't think we need to get into that so much. So the big points from all of that, all of those curves are that the optimum flow ratio is roughly between 70 to 80%, say 75%. The ideal COP inverse varies between 250 to 300 watts per watt, and the real COP inverse optimums are between 1750 and 1950. And the best real process performance occurred at 45 NTUs and 12 atmospheres, which was around about 1800 watts per watt. So that's kind of what we're after out of this whole thing. We'd kind of like to know where to operate, how to design this, and where to operate it at. So this basically tells us that we can, it should be realistic to design a small system like this that we can get 1800 watts per watt for the COP inverse, and to operate it around 12 atmospheres, and to probably use somewhere on the order of 35, 40 NTUs. The other thing we want to look at here is as I mentioned, we looked at exergy. So exergy will give us an idea of, if you put in a megawatt worth of power, where is all that power going? What's utilizing it? Ideally, if you put in a megawatt of power, you'd like all that megawatt to go to your load, but in reality, that's not what happens. So we'll look at that. This is I'm not going to cover the first three in detail, but these are the ideal COP inverse. This gives you an idea of the distribution. In all cases for the ideal one, which again was you're not considering considering only the exergy flux supplied to the cold box. We're not considering actual input power. And so in all of these cases, the largest fraction is going to be your load, and the smaller fractions will be the other components. And in those cases, it's the largest heat exchanger which has the largest loss. It's the largest user of that cold box's availability. So what I want to get to is I want to get to the distributions for the real process. So in all these cases, what you'll see is the largest percentage is going to be associated with the vacuum pumping system. Very close to it is going to be the 4K cold box system. I don't think this was a big surprise, but it does confirm what we would otherwise think. And a much smaller fraction of the availability goes to the screw compressor, and then about the same order that availability goes to the 2K cold box. So as with any pie chart, of course, the sum is 100 here. So as you can see, the load is only, of the total input power, only about 8% is going to the load. This is that was the simple refrigeration recovery. This is the one that has the integrated purifier, and then this is the one that has the varying heat exchanger injection. Okay. So these are some more subtle, smaller issues related to that, and that is, in heat exchanger, you basically have two components of losses. You have losses due to temperature difference and losses due to pressure draw. Those are two mechanisms where power, effectively input power, is being lost. And the point of this chart here, right, is basically to say that number one, the power loss due to the heat exchanger was relatively small, but this gives you basically an idea of what it is. So of the power loss to the warmest heat exchanger was 13 kilowatts, and 58% of that is due to the temperature difference, and 14% is due to the pressure drop, and 35% is due to the heat. nothing else, just gives you an idea that you can actually quantify input power and its usage this way. All right, so this curve right here is a little bit of an involved curve, but it's actually a very interesting curve. This is the warmest heat exchanger, or this is the coldest heat exchanger. This is basically the 4 to 2K heat exchanger. This is the NTU, so this is the length of the heat exchanger. This is the warm end of it, this is the cold end of it. And this axis is representing the stream temperature difference, and it corresponds to this green line right here, which you can see with this arrow. And this axis over here corresponds to the stream capacity, which is the mass flow rate times the specific heat. And this magenta curve is the high pressure stream capacity, and this blue curve is the subatmospheric stream capacity. So you can see if this were an ideal heat exchanger, these curves right here would be flat. So they're obviously not flat, and especially the high pressure stream, this is very nonlinear. And what's interesting too is that this the stream capacity is very high in the beginning, goes to a minimum, but then as it gets closer to the lambda point, it actually starts to shoot back up again. So that's kind of the idea why we were trying to vary the injection point, is to see if we could somehow match the cooling curves a little bit better because of this effect right here. This is This is the warm heat exchanger. So this is from same idea here. This is at 300K. This is down to 4K right here, and this green curve is the stream temperature difference, and this is the stream capacity. So again, if helium was an ideal gas throughout the entire thing, these curves, this one and this one, would be completely flat. We see that that's true for the low pressure stream, but not for the high pressure stream. And in fact, this is right around the area of around 15 Kelvin, where that, in one of the earlier slides, we saw how the CCP shoots up. That's right in this region right here. That's what's happening. Cover most of that. Something that's worth mentioning too, the ambient vaporizer that we have that basically is taking the flow out of the warmest heat exchanger. Now the flow is going to come out of there fairly cold, and there's actually a good deal of duty on that. But in terms of the actual power loss, it's not a significant contributor to the overall power loss. That's what I'm trying to mention in this part of the slide right here. So, summary, as I mentioned, 1,800 watts per watt for the real COP universe looks like it's achievable. That corresponds to an ideal COP universe of 250 watts per watt. This is about 3.5 times better than direct vacuum pumping, and about 2 times better than JLab CTF. And we'll mention again, that as kind of a lead into the next talk that will be done by Matt, and that is that again that we mentioned the need for a purifier, that it was a good idea to plan one to handle either the full flow or at least a slipstream of it, and we, as part of one of the configurations we studied one that basically was an integrated purifier. So firming this up, this is actually our design of our purifier that Matt did, and it's 60 grams per second. That's my sales pitch for next presentation. I think I've mentioned that already. want to mention too again that the efficiency of the 4K plant is a major factor in 2K efficiency. And then this chart basically just summarizes everything. It's a quick summary of all of those charts and plots. And I worked through here on this slide. You can work through it if you want. Basically what I did was I took that data and worked through an example on how to use it. But the caution note that I would give on that is that you can calculate a number, but the number that you calculate, you may not be able to find a vacuum pump that fits precisely that size. And that's typically going to be the case for compressors and vacuum pumps. They don't come in continuum sizes. So there is a note on caution to that. And as basically in conclusion here, and I won't carry on too much longer, but one might ask the question, so why not use direct vacuum pumping? In fact, why not just supply it from a dewar and use a vacuum pump? And so we looked at that. I want to look at a cost comparison of that. So the first case that we're looking at is using a direct vacuum pump being supplied by a dewar. The second case we'll look at is the same, except we'll add in a heat exchanger at the cold end, that 4 to 2K heat exchanger we've been looking at. And then the third case we'll look at is, the third case will be that we're doing direct vacuum pumping, but we're using a liquefier, a commercial liquefier. Fourth case, we add that heat exchanger in with the liquefier. Fifth case is just kind of a reference case. It's what CTF should operate like. And the sixth case, if you implemented one of the configurations that we studied in this process study, what would that be? So assume the nominal load of 180 watts. That's basically what CTF's K load is. And assumed a cost for the liquefier of roughly $300,000 per gram per second, and a cost for the vacuum system of $60,000 per gram per second. If these numbers vary a little bit, it's not going to change the basic point. It may change the specific numbers, but it won't change the basic point. So those are just the numbers that I happen to use this time. And so this first line here basically is a total cost. In each case, the capital cost required for each one of these. So as you might expect, the dewar case is one of the cheapest ones to do. These two are the dewar cases. This one here is the direct vacuum pumping, but using a commercial liquefier. So this cost is going to be more because you've got to buy a 4K liquefier. And then this case right here, this is CTF, and then this one is one of the process configurations that we studied. So you can compare and see that just the capital cost between one of the process configurations we studied in CTF that is about half the capital cost. Now, what about operating costs? These are kind of on the order of what we're paying for stuff. And so the operating cost, I put in two columns down here. One is if you operated it a quarter of the year, and then one if you operated it for a whole year. So we'll just look at the one for a quarter year. If you operate these dewar using a vacuum pump for a quarter of the year, you are spending $3.5 to $2.2 million a quarter year operation. Not to mention the fact that you're blowing helium off to the atmosphere. Helium, I think, as we've talked about, is a very valuable resource. So that's not a very good option on many levels here. Case 3 and 4 are the cases with using a commercially bought liquefier, but not just using direct vacuum pumping. And then this is CTF, and then this, of course, is our proposed one. And as you can see, that the operating cost for this is half the operating cost of the CTF. basically just summarizes what we've looked at. What are your operating costs for using a liquid helium newer? 2 times more than the capital cost required for one of the proposed 2K configurations. And the capital cost for direct vacuum pumping versus using a 4K liquefier is 2 to 3 times the capital proposed for one of the 2K configurations. And roughly about the same in operating costs. That ratio is about the same. So if there's any doubt on what to do for a 2K system, I hope that kind of gave a general direction. So in conclusion, just wanted to throw up a few things, kind of listed these out as ideas for further study. Characterization of the isothermal efficiency for various vacuum pumping systems. We don't understand that very well. We know what it is for ours. We got a good idea for ours, but in general, for a general vacuum pumping system, that don't really know that well. But that's also kind of hard to say to quantify because some of that information is going to be proprietary. But it is very key to doing a process study like this. The other one is testing some alternate heat exchanger designs. Ones that both have a very high heat transfer but a low pressure drop, which is obviously very key for some atmospheric process like this. One of the ones that we're looking at is basically a wire fin tube with tall wire fins on it. And we're in the process of evaluating that. So that's all I had. If there's any questions, happy to take them.
Any questions?